All right, let's get started. Thanks everyone, and thanks for waiting. I didn't want to start before 3:15 because some people might come then, because I said we'll start them. And yeah, sorry for the delay today. I had a workshop on grant writing, so I had to kind of attend that. So I couldn't really start on time today. And today we are going to talk about MapReduce. And this is basically going to be our final lecture. Next time we are going to do the recap you wanted in your mid-course feedback, where we are going to go over the topics we had talked about in the second part of the semester, which will be part of the exam you'll have on May 3rd. I will repeat it on Wednesday, but I will also say it now that just because we are going to go over and do the recap together, that doesn't mean that that's replacement for studying for the second part of the exam. So not everything I say there is like, okay, only that can come to the exam. But we will go through the main theme. So a lot that's is the very relevant for the exam will be covered there. Okay, so I have posted yesterday the final homework. It is a little bit simpler and more straightforward than our other homework. So although you have like 10 days, I don't see any problems with completing this homework on time. It is all about PageRank, and just you need to implement the power method iteration with teleportation we had talked about last time, and you're going to apply to the small graph of 10,000 nodes that represent web pages, and you will get only the information about edges, and then you'll need to find the PageRank scores for each one of the web pages. In the bonus assignment, you can work with the full version of that graph, which has 800,000 nodes and way more edges, which is actually the part of the data that Google had released in 2002, so over 20 years ago. So it kind of resembles what should be an actual data, actual web pages and edges between them. But of course, the full graph is more finicky to work with, so you'll need to find more efficient approaches if you would like to work on a bonus assignment. As you know, today you need to submit your posters. After the lecture, I will go over them and quickly just check whether things look all right to me. If I see that there is something critical to be changed, I will give you feedback tonight. And then tomorrow you need to kind of go over and fix those things that I had requested. My feedback today will be all about, like, if you have like huge chunks of text, for example, I will most likely tell you, please make an itemized list from this, because we can't really have, paragraph to read when we have a poster. And you will need to do that by Wednesday, 9 a.m. And then I will put all the posters to batch print. And our poster session will be on Monday. I will talk more about the logistics of that next time, and just repeating that our final exam is on Wednesday, May 3rd at 3:30. So 30 minutes later than our usual start. Okay, so as I said, today we are going to talk about MapReduce. But yeah, I should have stopped before I went through the next slide. Any questions about the deadlines? Okay, so today we are going to talk about MapReduce, and the reason why we have MapReduce, which is kind of like think about it as a system. It was produced because we are dealing with huge amounts of data. If you decide to work on the bonus problem or homework, you will kind of see how quickly things can become very slow. And the slowness of algorithm is not the only problem. The other problem we might encounter is that our data becomes too big to entirely fit into the memory. So, for example, if we have, which is totally conceivable these days, 10 billion web pages, we have way more than 10 billion today. And if the average size of a web page is 20 kilobytes, then when we multiply 20 kilobytes with 10 billion, we will get that the size of the data is 200 terabytes. Another metric that's relevant is that what is the bandwidth of reading the data from the disk, and if we use the number of 50 megabytes per second, then time to read the data, this 200 terabytes of data will take 4 million seconds, which is 46 days. So it's really, really slow to read all of that data. And we do need to read data if we want to make a computation with it. So MapReduce had emerged from this situation where we have enormous amounts of data, and we need to deal with the fact that it's huge and that reading the data might take a very long time. Okay, so to kind of to some of you, immediately parallel computing or distributed computing might come to mind. And the idea behind cluster computing is that instead of having, one CPU with memory where you read the data. Oh, excuse me, just a moment. So we have CPU and we have memory, and these two things are working together to do our computation. Well, we can have multiple of these and we can do stuff in parallel, right? If we have thousands of disks, then our 4 million seconds become 4,000 seconds, and that's about an hour. So things can get way quicker if we have multiple disks and run things in parallel. So, okay, that's one solution to our problem, but what kind of challenges might we occur if we do this? So first of all, nodes can fail. And this problem of nodes, and think about nodes like CPU and memory, them failing is not so problematic if you have one of them, because one node can go without failure for 3 years. So if you encounter your failure problem only once in 3 years, then it's not a huge, such a huge issue for you. If you have thousands of servers in clusters, so thousands of, let's say, disks and CPUs, well, you might encounter one failure a day, and you might still find mechanisms how to avoid that, or maybe that is still not a huge issue for you. But if you have 1 million servers in a cluster, then you will encounter 1,000 failures per day, and this becomes an issue. So more of these nodes you have, the more parallel you try your computation to be, which you want, because you want your computations to be fast, more failures you are going to have. And think about when I talk about how many nodes we have, think about data centers where we have for really 100 million nodes. I think in 2011 Google had in its data center 1 million. So you can think about how many we have today, 10 years after, probably way more. So we probably have these days more than 1,000 failures a day. So it's kind of, I'm constantly mentioning Google in this context. And the reason is that this MapReduce had emerged from Google engineers. For example, one of them is Jeff Dean, who is now the head of Google AI. So these kinds of problems were really emerged from that, dealing with huge number of web pages and, everything that had happened when data had become bigger in early 2000s. So if we have a problem of having 1,000 failures a day, which is a big problem, then these two questions emerge: how to store the data and keep it available if nodes can fail, and how to deal with nodes failures during a long-running computation. So the first question is relevant because if you're storing your data on one node, if you can even fit it on one node, and what happens if that node fails? It might do something weird to your data. It might even completely destroy your data. And that would be terrible, right? Especially if you've been collecting it through user interactions for years, which is kind of like the business of these huge tech corporations. The other question emerges from the fact that, okay, now you have been running this huge computation. Remember, I told you that it could take 46 days just to read the data. Now imagine how much longer it could take to do something with that data. And imagine you are like doing the computation for days, and then in the last step, your node fails and your entire computation is destroyed. This is all too well also to anyone who is working with deep learning these days, where our jobs also take sometimes a couple of hours, if not days, and we have our other techniques to deal with that. So the first challenge, just a reminder why I'm talking about all of this, it's that we're talking about challenges of cluster computing. So nodes failure is one problem. And we want to find a system where we can store our data such that if nodes fail, we don't destroy our data. And we have a system where if we had a failure of a node, our computation is not complete rubbish. All right, so the second problem of cluster computing is the network bottlenecks. So we can have the bandwidth of our network to be 1 gigabyte per second. So moving 10 terabytes of data takes approximately 1 day. So we don't want to move our data too much. We want our data to be stored somewhere, and we don't want to transfer it from one node to another node. So we want our data to be kind of static and bring the operations to the data rather than the data to the operation. And the final challenge is that distributed programming is very hard and very finicky. So anyone who had ever implemented something in parallel probably knows what I'm talking about. It's just hard, and I hate it so much. So for us who work, in NLP research, we typically don't use, if you don't do pre-training, we don't use such enormous data sets. And because this problem is so hard, in NLP, there is a trend that we make our GPU memory larger and just use one GPU for all of our computations. So A100 with 80 gigabytes of memory are not super standard, but we use them for our jobs, which is kind of, I would say, silly. And it really speaks for how hard distributed programming is. Our MapReduce will take care of all these three challenges. We are going to store the data redundantly on multiple nodes. So if if one node fails, we won't lose all of our data because we have replicas of our data across many nodes. Yeah.
What is like having algorithms to enter our data in case like this?
What kind of algorithm?
Like having algorithms? No.
I don't know. Yeah. So this is kind of like 20 steps of degree separation of what I actually do, like hardware and these kinds of stuff. So I don't know much about this stuff. Yeah. Yeah, but you can maybe send me that question, and I can ask other professors who know more about this. Okay, so the first thing is to store the data redundantly on multiple nodes. And so if our node fails, then we don't lose entirety of the data. We are going to then have in this MapReduce system, everything will be designed such that we don't move the data around. Rather, if you need to, you store the chunks of your data on a certain node, and then you call some operation to that node. So we say kind of like you bring the operation to the data instead of other way around. And the whole system, this whole MapReduce system, which is available through Google software or Hadoop software, is designed such that programmers don't really need to understand the complexities of the distributed programming. So all of that is hidden somewhere in this system, and the programmers just need to think about how to solve the task with this MapReduce paradigm, which I will show in a bit. So all the details of distributed programming are somehow hidden in the system. Okay, any questions about like why are we talking about MapReduce? Anything that I said so far? Okay. So the first step was that we are going to store our data redundantly on multiple nodes. And we're going to do that through something called distributed file system. So maybe some of you know for two of them, Google File System, GFS, or Hadoop Distributed File System, HDFS. So there are these kinds of implementations of this distributed file system. The principle behind distributed file system is that, as I said before, we want to we want our data to be static. We don't want to move it around. And for that, it's also important that our data has a certain property, and that's that it's rarely updated in place. So, for example, think about web pages. If we have some kind of data structure that represents all of our web pages, let's say just a list of every page we have so far, you will rarely actually update the web page you already have in your list of web pages. You're just going to add a new page to the list. So there is a lot of append operation and little like update information I already know. So that's just the nature of this data and nature of this problem or when we talk about web pages and search engines. And then this data with these distributed file systems, as word distributed might hint, is going to be kept in chunks spread across machines. So spread across machines is this distributed part. So you might have here, let's call this. So I will use word node and machine and so on interchangeably. And you have here some node. So 1, 2, you might have n of them. And you have your huge data. And you're going to keep chunks of this data on these different nodes. So just for visualization, I'm going to chunk it like this. So we have here 6 chunks. And you're going to spread these 6 chunks across your machines. So let's say we have this one, which is a green one. You might put it onto the first node. However, remember that our goal was that if our node fails, for example, here node 1 fails, it's completely destroyed. You don't want to lose that data. So that chunk is going to be also placed 2 to 3 times on different nodes. So you might put it on node and here, let's say. Okay, so that's the first important thing. You are going to spread your chunks of data across machines, and you are going to replicate each chunk 2 to 3 times on different machines, such that if one of them fails, you haven't lost the entirety of the data. And now, reasonable question could be why 2 to 3? I don't really know. I suppose that people have used 2 to 3, and it seems to be the case that if simultaneously nodes fail, you won't have all 3 of them failing at the same time, I suppose. Was there a question over there? No, okay. And then remember when I told you we are going to bring the computation to the data? What I meant by that, you are going to design your computation such that you split it in smaller subjobs, and each one of these jobs is going to then work with the chunk of data. That's kind of the principle of parallel computing that is quite intuitive. I don't think there is much to say about it. So your big job will be to split, and here you are going to send your job to calculate whatever you are calculating on this chunk of the data. So we never move the data around. That's why we don't have that issue of whatever is the network bandwidth might be a bottleneck for us. And when we talk about distributed file system, you also need to know about two more things. That's master or named node. That's a node that stores metadata about where files are stored and replicated. So that's important thing. And there is something called client library that talks to this master node to find chunk servers. So this master node will also be replicated a couple of times. Okay, and that's basically all about distributed file system. I think it's pretty intuitive what it is. I think one thing I didn't write here, and that's also the case, is that if you have second chunk and you place it, let's say over here, then actually no. If you have these replicas here, I used green color. So replicas of these nodes won't be placed on the same node, of course, because that would go against the idea behind having replicas, that if some of these nodes fail, you don't want them to put them on the same place. Now the node fails and all of the replicas had failed as well. So that's something you need to take care of as well. Okay. And then the MapReduce is very, very simple from here. So I will use the example of word counts to illustrate what you do once you have this kind of data situation. So MapReduce consists of map and of course reduce operation, and there is this intermediate thing called group by key. So imagine we are having a problem of calculating word counts. So we are going to first have our data with our distributed file system. Here is some textual data. It's going to be split across different nodes, right? So we are going to have a chunk of this data on one node and second node and the third node. Okay, now map operation will extract whatever information you are interested from each one of these chunks of data, but such that you also record what is the kind of like a piece information. So in the word counts example, your key is going to be word. So here, let me actually use concrete sentence because I think it might be clearer like this. Okay, can you give me a short sentence? The cat is jumping. Thank you. Okay, so imagine that each one of the chunks of data is one sentence, and then let's say the other sentence is, I don't know, the cat is sleeping, which is exactly what my cat was doing this day. Okay, so we have these two chunks. In the map operation, we are going, so our problem is counting words. We need to extract a key. Key is here word and the count. So we'll have the with count 1, cat with count 1, is with count 1, and jumping with count 1. That's from the first chunk of data. And now from the second chunk of data, we do the same thing. here is capital D. D with 1, cat with 1, is with 1, and sleeping with 1. So you do the operation at each one of the chunks of data separately. Now with the group by key, you are going to take all the keys correspond that are the same and kind of group them together. So you will have one group which will be the and 1, and here that's in the first and also the first in the second chunk of data. So that's going to become first group. That's grouped by the key the. Then the second group will be cat 1, and again we have cat 1 in the second one. Then we have is and 1, is and 1. That's the third group, and we have jumping 1, and we don't have jumping in the second chunk, so that's the only group here, and sleeping as well will be the last group. So we have 1, 2, 3, 5 groups from these 2 chunks of data. And then the reduce operation now needs to basically aggregate the operation across the across each group. So if our goal is to find the word count, which kind of operation we should do across the values of each one of the key value pairs here? Sum, yeah. We want to know what the count is, and now we just sum the corresponding values. So the cat and is are going to have value 2, but jumping and sleeping will have 1. Okay, so just to go over everything one more, the goal was to calculate word counts, and imagine we have enormous data sets with text, and we want to do this faster. So we split our data into chunks using our distributed file system, and imagine that we have so many nodes that we can actually put one sentence at each one of the nodes, which is not going to happen, but for the illustration, imagine that. Now, in our first node, we have the sentence, the cat is jumping. Then in the second node, we have a data which is just one sentence, the cat is sleeping. From each chunk of the data, from each sentence, we are doing map operation, which produces key value pairs. Here, we as programmers had decided that key will be word and that the value will be the count of the word in that sentence. And we are going to do that for each chunk independently. Then in the second step of MapReduce, we are going to group our keys. So across different chunks, we are going to take every pair that has the same key and put it into the same group. And in the final step, we are going to reduce the values. We are interested in the word count. So we as programmers say, okay, here we need to sum all the values. And this is how, in the end, we get the word count, but by using multiple nodes. And I think obvious question here is this. This looks very, very simple. And it might be so simple that it's kind of confusing what's happening here, maybe at the first glance. And the point here is that with word counts, it was kind of straightforward to see how we can turn our initial data, how we can split it to different nodes, how we can then extract keys, and how we can, from values, reduce that values to get word count across the entirety of data from each one of the chunks. But for many problems, finding this design, finding what the keys could be, and how to then reduce them is not straightforward. And that's the kind of the crux of applying MapReduce to a new problem, finding what those keys could be and how you can reduce them. Okay, you had a question.
Part of the process to be replicated.
So we are not replicating the process. I mean, we are and we are not, but I want to clarify where I used the word replicated. So initially you have your data, and here the data, imagine that it's just a huge collection of text. Let's imagine we had crawled the entirety of web, and now we have terabytes, hundreds and hundreds of terabytes of textual data. So that's your data. You're going to split it somehow. And for the sake of illustration, let's say you just split the text such that each sentence is a chunk of data. And you're going to put each one of these sentences to different nodes you have. And let's say you have as many nodes as there are sentences in your text. Chunks of data are replicated. Yeah, so you're going to have different ones on different nodes. And then you are going to call your job. Your job in this illustration was to calculate the word counts of every word that is in this initial set. But now you have split your data across these nodes. So you're going to take one replica of your chunk and call operation to that chunk. So in the word count example, that operation, first one is map. First, you are going to extract key value pairs where key is word and value is count in this chunk of data. But you won't do it for every replica. You are going to do it for one replica of the data. The other replicas serve just if in this process, imagine that now the node where we have the cut is jumping had failed. And imagine it had failed so badly, it actually destroyed this sentence. Now you want to repeat not only the operation, but you need new data, the same data from somewhere else, because on that node it was destroyed. And you're happy because now you have that replica on another node, and you will just repeat that one single job, subjob, on that other node where your replica is. So that's how it's failure safe.
Sometimes in the middle of the operation or in the last part of the operations, they're not fails.
Mm-hmm.
So I think it might be better to make replicas in the last parts, like group by key or revenues.
Yeah, I don't think about these steps now of map, group by key, reduce as the same steps you would have if you have done the entirety of your job in on a single node. It's kind of different, right? Because imagine if you had only one node and you have this entire data on that one node, and now you have kind of went over million of sentences, and now your computation fails for some reason. Let's say node fails, you have lost everything, right? Here in these steps are smaller, right? Because and they're not exactly the same steps as before. So here in one node, you have just one small chunk of that data. So if that node had failed, but others did not, you just need to repeat that small computation, which will probably take just a little fraction of your time. But everything else is there, recorded, and waits for you to repeat that one job, which once you repeat, you can do the rest of it. Unlike before, where you just completely lost everything. Yeah. Any other questions? Okay, so basically that's it. There is not much more to it. And as I said, when we take the word count problem, things are very simple because it's kind of straightforward what the key and value pairs should be. when you have a completely new problem, situation can get very complicated, especially when you work with more complicated linear algebra operations. Yeah, and I also want to emphasize, so we said MapReduce will solve three things. One is that first, the problem of our data being destroyed. I think it's clear that with distributed file system, how this is avoided. We said we are going to move, we have a problem of network bandwidth, and moving data around is slow. So we never move the data. The data is always, it is split on chunks, and once it's split, it's just there, it never moves. And we are placing our sub-job to that node where the chunk of data is, and then we collect the outputs of smaller jobs into kind of like one big outcome. And then I said there is this problem of distributed programming, and that's kind of hard to illustrate, but basically in MapReduce, in the actual software, when you use it, you don't need to worry about, so you have that master node and everything, but once you figure out how to approach your problem as MapReduce problem, you don't really need to worry about how you are going to distribute that subjobs you have designed into these different nodes. That's going to be taken care of you. And that's why it's, as the whole system is much simpler to use than if you would do this whole distributed thing yourself. Yeah.
Is this MapReduce concurrent? So we have another document that we had in the middle of this complication. Could we just like basically a date in the middle?
So you mean like, okay, you have your data initially, and now more data have come, and you wonder, can you add more data to it? So I want to reemphasize point that this is designed for data that's static and that doesn't change much. So if you're just appending more data, I don't think it should be an issue, because see it with, and I think it depends on what is the thing you're trying to calculate as well. If your computation of depends on what you calculated before, think about maybe matrix vector computation, then it can get tricky. But in the word count example, where if you add more data, you can add another job, right? And you can just update these values at the end, right? So I don't think in this example it matters, but I don't think for any kinds of problem you might have, might be so simple.
What kinds of data is this usually used to store?
You mean what kind of problems
Yeah, I
are?
guess I'm just thinking like about web pages versus like word counts, and like if you were storing like web pages or something, like that's useful to get the content of the web page. But if you just had like word counts of just like a bunch of web pages, like how do you reconstruct what it is that you want from the feature that you like selected for your map?
Okay, let me try to map that question into my head. So you are wondering, why would this be useful? Is that the question?
I guess like what data is it used to store, and like what feature that you're picking, like as opposed to like word count, are you using that is actually useful?
So word count is useful. So this is or if you go back to the original MapReduce paper written by those two Google engineers, it is the actual problem they were trying to solve in the context of search engines at the time. So word count is a relevant feature for in the context of finding the, whatever might be interested to people who look at the web pages and their importances. So I don't know, maybe you feel like it's not important, which is okay, but it has been used in the context of web pages. So I guess I can't defend it more than that. So yeah, that's what I have. Yeah.
So is it used like for searching or like doing something and not for rendering the web page itself?
No, it's not used for rendering the web page. So this is all about, given that you have word counts, what can you do then with it? And so
I think it might be useful for things like still, which pages based on how you use the words and the frequency.
Yeah, I mean, that makes sense to me. So I don't know, we were talking about this example of term spam, where people put certain words in their web page a lot of times in the background, in the color of the background, just to make their web page score more highly if you search for that exact term. So maybe like pizza, and then you get that page, whatever you had actually asked for. So here, knowing that a certain word occurs way more than other words is a useful feature. And I think that's what you were referring to, right? Yeah. Okay, so let's move forward. We will now go over another example that might be a little bit more, agreeable about in terms of importance. So we'll go back to our PageRank, and let's try to see where could something like this be useful. So remember the power iteration method for finding the PageRank vector R. Which operation was repeated and also seems intensive if we have huge number of web pages. So our transition matrix is large. Do you remember what was the main operation in each iteration? Exactly. Yeah, that was basically the only operation we had at every step of the power iteration method. We have R. Oh my God, this is ugly. R equals M times R. And remember, M is the size of number of web pages times number of web pages. So it's a huge matrix, right? And the vector R is of the size number of web pages. So this is a huge matrix and a huge vector. We are doing this huge matrix times huge vector multiplication, not once, but as many times until we converge. And convergence meant that our new PageRank vector and our previous PageRank vector didn't change. The difference between them didn't change much. So we can now think about, okay, how we can maybe split this computation in a way that we also handle the memory issue. So these are two situations we are going to look into. So first, we are going to pretend that we can fit our entire vector, PageRank vector R into the main memory. And let's see how. Let me change color. So here, the ith component. I'm so sorry. I don't know how to not flow this. Okay, the ith element of the vector PageRank vector R is obtained by taking the ith row in our matrix M and multiplying that ith row with the entirety of our vector R, right? That's how we get the value, the ith value in the new vector. So we can write that as a sum of j from 1 to n, when n is number of web pages. And then we have mij times rj. So our ith row is fixed, and we are going over the values in the ith row multiplied by the entirety of the vector R. So now, let's assume that R fits in the main memory. We can then, and let's assume M does not fit into the main memory. Then we can take our matrix M. We can put its values Mij across nodes. So we can basically choose any kind of split of our data M here. And then on every node, we are going to, as our value, as our key, we are going to use the row, the value of our row I in the value mij. So that's our key, what was burned before. And our value is going to be mij times rj. Okay, so the key is the row. All right, so this is basically our map operation. And if I'm interested to find what's the value ri, what should I do? Okay, let me go over. Oh, do you want to go ahead? Mhm. So the first thing you said is right. So you select some key, you are going to group by key like we did before. And then we are going to get values 1, mi, excuse me, yeah. So mi j times rj. Let me just see, something is not right here. So on different nodes, we are going to have different values j, right? Maybe that step wasn't clear. So let me go over this again because I confused myself and you in the process. So we have our matrix M, and our matrix M has values mij. We are going to put these values mij to different nodes. And on every node, we are going to calculate mij times rj. And as a key, we are going to select whatever was the value of that row in mij. So I hope that's clear. But we are going to have on different nodes, if we had j went from, remember, 1 to n, basically imagine that the values of this row mij were spread across different nodes. So we have node 1 might have mi1, node 2 might have mi2, and then node n might have min. Now I put this, I put them sequentially into their nodes, and I also assume there are as many nodes as there are, whatever is the value of n, which are all just assumptions I'm making for the illustration of this. But the point is that you take the row and you put the values across different nodes. And at each one of these nodes, you are going to then compute this value over here. So here j equals to 1. So you will have here 1 because this is I. No, sorry. We are going to have, we didn't name I. So I is going to be here as our key. And then we are going to have mi1 times r1. Then the second node have j equals 2. Then we'll have as a value, again, our key will be I, but the value is going to be mi2 times r2. And all the way to the last node where we have j equals n, and then we'll have a key, again, I, but the value will be min times rn. Okay, so this was our map operation for, only for a certain row I. And now we need to group by key, and here they are kind of already grouped because we just focused on one row. And the next thing is reduce, right? We want to find the value of Ri. So if I want to calculate the value of Ri, what should I do with these values? Sum them, right? So Ri is given as a sum of these factors over here, which are exactly factors over here. So you just need to sum these values that you can find by the key, right? So if we had another row, K, we would just find all these pairs where the key is K, and we would do the same thing. We would just sum of that group of key value pairs where key is K. And that's how we would find every single value dimension in our vector R, which is, R1, R2 to Rn. Okay, so this was a little bit bumpy on my side, so let's see whether this is clear now. Okay, yeah.
So if we were doing this with the whole matrix, we would have, the one would have every value equals 1, so every column. The whole column, sorry.
Yeah, so here in this version, it's not really important where we place each element of our matrix Mij. We never really use that property, right? The big assumption here was, though, that we at every node had access to the corresponding element in our vector R. So we had to have vector R on every single node. And everything else didn't really matter. But that's a big assumption too that we have made, and that's what we are going to talk about next. Yeah, so this step here, where we place Mij to different nodes, we didn't really use any special procedure about how we are placing them to different nodes. Maybe I can write that down. Different nodes, maybe randomly. And here, I'm just trying to find R is available on every node. Okay, so that's a big assumption that our R is that we can fit it in its whole entirety to node, because our R is the size of the number of web pages, and it's not going to be sparse vector, because remember, this is a vector where we have our importance scores. So each one of the web pages will have some value for the importance score, and we won't have lots of zeros inside of the PageRank vector itself, although we will have a lot of zeros in the matrix M, which is, I won't talk about it, but that's another thing we can exploit, that the matrix M is rather sparse, because we don't have, remember when we were talking about how the web looks like, we have said that there is maybe like a strongly connected component, but otherwise things are not super well connected. So besides that strongly connected component, we have lots of blocks of matrices M where we have sparse vectors. Okay, so this is what I said already. Now, what if is we have a situation too where R is too large to fit in the main memory. And when I told you that, okay, the crux of MapReduce is to just figure out how you can attack your problem through MapReduce, this kind of goes along, into that, right? Now you have R that is too large, and you need to kind of wonder, okay, how can I still use this MapReduce framework but not fit R into the main memory, and not assume that in every single step of map, I can actually use the entirety of R. And here people have developed another way to handle this matrix M and vector R. So our matrix M and our vector R, are going to be divided into chunks like this. You're going to use, you're going to split your matrix M column-wise into I'm so bad at drawing straight lines. Okay, so each one of these chunks will have the same number of columns. So you are dividing your matrix M into these vertical stripes where each one of these stripes has the same width. Okay, so here we have same number of columns. And you're also going to divide your vector R into the same number of chunks. So here 4, but you're going to divide vector R horizontally. And now, remember matrix to matrix multiplication? We have seen it here. Is you take the row and then you take the entire vector and you get I position in the new vector. So now here you're kind of splitting this sum into these chunks because let's focus on the first row over here. You would need to divide. You would need to take this entire row and sum it with this entire vector to get the first element of the new vector. But now we are going to take this chunk of data that's going to be on one node, and that chunk of data will have access to this first chunk in the vector R, and you will still do the same thing. You will still calculate these kinds of key value pairs, but just using the smaller chunks. And now in the end, when you do reduce, you need to collect them and again sum them up. So let's try to maybe write how this would look like. So node 1 will have, let's say, row equals to 1 and columns equals to, let's say we have n to be 16 just to make my life easier. Then we would have here 1 to 4. Here we have node 2. You have row 1, columns 5 to 8. Node 3 would have again row 1 and columns to 12. And node 4 would have row 1 and then columns 10 to, 13 to 16. My brain is dead. Okay. And now here, you would also from row 1, from vector R, you would have R 1 to 4 and R 5 to 8 and R 9 to 12 and R 13 to 16. And basically you are doing the exact same thing you have done here, but using this portion of the matrix M. So you have values Mij that are defined through the row equals 1 and columns 1 to 4, and you have your R from 1 to 4. And so on. And you would do the exact same situation over here. you would just sum the values and you would get what is the ith position in your vector R as you have done it in this step over here. Now, this was where we have R that fits in the memory. This is a situation where R is too large to fit in the memory. There are more and more situations people think of in terms of PageRank and MapReduce, and where they continue to kind of refine this MapReduce paradigm. So they might notice, okay, matrix M needs 2 sparse, and I might want to use blocks of it, and so on. So there is more and more and more to it. I won't go further. I just wanted to illustrate these 2 ways because they kind of go along with these 2 obvious main problems. Where matrix M is too large, but okay, maybe R is not too large, as we have seen in situation 1. And then in situation 2, where our M and R are too large, but we don't really kind of consider other aspects of the matrix M that they are too sparse. If you go to the Mining Massive Datasets book and go to this chapter 5, which talks about PageRank and link analysis, in one of these sections, you will find a section that says efficient computation of PageRank, where you can find even more ways to use MapReduce to kind of implement PageRank more efficiently. And that's when I mentioned in the beginning of the lecture, I said in one of the bonus problem in the homework is basically try those approaches for the graph with 800,000 nodes. So if you are interested to maybe play around this stuff, you can explore that in the bonus problem of the assignment. Now, because we kind of rearranged our schedule a little bit, and we said we're going to introduce that recap, we don't really have time to talk about another topic about graphs that I had been thinking to present before. And this is about community detection. So imagine, your whatever social network you might be using, and this is going to be an example of your social network graph, where each, let's say we focus only on you, and let's say we focus on, maybe you are using, I don't know, Facebook is not really a thing, but let's pretend it's a thing. And we can maybe make a graph where we take only people that follow you. These are our nodes in the graph. And we have link between nodes if those followers of yours are actually following each other. Maybe if at least one of them is following the other. So that could be a graph. And in this graph, we might find some communities. So maybe we would find nodes in your graph that are connected, that this represents your high school friends, or maybe we find nodes in that graph that represent your whatever friends you have from your hobby. Maybe you are, I don't know, playing basketball, and now these are your basketball friends, and then we might have your college friends. And what's interesting about finding communities in these kinds of graphs is that they can overlap. So think about, let's say you have your college friends that you also know through some hobby, like maybe, I don't know, chess or something like that. This is a bit particular situation, because if you remember, we have talked about spectral clustering. So for you, if I want to find a way to find communities in a graph, your immediate reaction could be like, graph, I have seen graphs before, and if I want to split the graph into groups, I kind of heard about that before as well. We have used spectral clustering, so I could apply spectral clustering to this problem. And you wouldn't be wrong, except that you wouldn't consider the fact that the communities overlapped, and the spectral clustering, we didn't allow that one node can be in 2 clusters, such as hierarchical clustering, right? Now you can say, well, then I will just use hierarchical clustering instead. And with hierarchical clustering, I won't work that example, but you can quickly see that you would merge 2 people that have nothing to do with each other. And it just doesn't work for this problem. So defining your communities automatically using spectral hierarchical clustering is not going to be the best way to solve that. And that's why this whole, there is a whole topic of just about community detection in graphs, which I will not talk about. I just wanted to briefly mention what that whole problem is. I did make a post on Piazza where I shared you chapter in the Mining Massive Datasets book, as well as the Stanford course that covers this topic. So if you're interested and want to learn more, you should at least go and see those lectures from Stanford. I believe there are 2 of them, but that whole course is about machine learning for graphs. So if you are really interested in this topic in general, you have way more topics covered there. And the course is from 2021, so it's not super old, not super outdated, and there are some very cutting edge stuff there as well. Okay, that's all. And then next time we'll do the tour of our second part of the semester. I will, as always, I'll be around for the office hours. If you have questions about your posters, come there. Okay. Oh, no.